Hello, this is Concrete Path, and let's go to this topic. Let's go for this topic. First part of that, first subtopic, we call it as relative density. That's relative density, or we can also call it as density index, and we can note it as in this way that this is your dr, and the result for that, this is actually the ratio. This is actually the ratio that E max minus E natural divided by E max minus E minimum. So this is the ratio of the difference of wide ratios in the max condition and in the natural condition divided by max minus E min. So let's try to get that what E max is. So E max is actually wide ratio of the soil, in the when the wide ratio is maximum, that means it is volume of voids by volume of solids. If the wide ratio is maximum, that means volume of voids is more as compared to the volume of solids. That means the soil is in the loose condition. Soil is loose. So void ratio of soil in the loose condition. And we have one more equation that gamma dry equals to G gamma W by 1 plus E. And if your E is maximum, at that condition, can we say at that condition, that means that soil is loose, so your gamma dry would be minimum, so your dry density would be minimum. So at that maximum E value, we can have gamma dry as value of minimum. So this is your in the loose condition, and similarly we can write E minimum is the void ratio of the soil in the densest condition, and your E natural, this is your E natural, that's in the natural condition. That's you are going to perform some test on a particular soil that's present in the field. So that's your, you can get the sum of the value of E. That's your actual value, that is the original value, actual value that you are going to get in the field, original field value of the wide ratio. That means at that point you are having some gamma, that's actually gamma field, or that's corresponding to natural condition, gamma natural. Okay, so this is the ratio, and this one is we use it for what you call as for the coarse grain soils. This statement, this relative density, we are going to use this one for your coarse grained soils. And we say that this is almost equals to, we have one concept of that relative consistency. And that's used for fine grained soils like that of clay. So relative consistency, we are going to study that also. So we say that your relative density for coarse grained soils is similar to that of that relative compaction concept for your fine grained soils, that's clay. So this you can write, this is similar to that concept. So for the coarse grained soils, your relative density is there, and it is similar to that of relative compaction for fine grained soils. And this relative density tells us the that degree of denseness or density, degree of looseness, degree of denseness, or degree of looseness. That how much is your that soil, is it in the loose condition, or is it in the dry condition? Because we are comparing because we are comparing that, you can see we are comparing our natural condition with that of maximum versus minimum condition. So we can get the idea that whether our soil is loose, in a loose state, or it's in a that what you call as densest state. So we can get the idea of that. And for that we have the table, that if I have a particular value of dr in the range, if your value of dr is in the range 0 to 15, 15 to 35, as a percentage, we are saying as a percentage, or you can keep as a fraction. We can keep as a fraction because we are not multiplying 100, so we can keep it as a fraction. Let's keep it as a fraction. So that's from 0 to 0.15, from 0.15 to 0.35, from 0.35 to 0. How much? 0. What was that? Why we kept that? Why we kept that? No. Yeah. 35 to 65%. That means 0.65. After that, 0.65 to 0.85. and after that greater than 0.85. Maximum value we can have up to 100%. So for that we classify the soil. We classify the soil according to these values we have. According to the range, we are saying the soil, if your value of dr is less, that means the soil is very loose. So soil is very loose. After that the soil is loose. After that the soil is medium dense. After that the soil is dense, and if the value is greater than 0.85, we say the soil is very dense. So very dense way right here. So soil is very dense. So this is the comparison sheet we can have, comparison table. And we say that if your value of dr is more, that means you are having more density. So more solids are filled in a particular volume. So it tells that if your dr is more, your shear strength is more. Your shear strength is more. Your dr is more. Your shear strength is more. And that packing is more. Voids are less. That means voids are less. We can say voids are less. If your value of dr is more, that means voids are less present in this natural condition. If the voids are less, we can say the compressibility is not going to be there. So compressibility will be also less. Compressibility would be less. So compressibility is because we can compress the volume because that was occupied by air. If there was less air, so we can say compressibility would be less. Compressibility is less. Because of dr is more, your shear strength is more and compressibility is less. So this is one more statement we can get. If dr is more, shear strength is more, compressibility is less. Okay, this was one more statement from this one. Now we say that how you get the value of Emax and Emin. We say that in one of the lectures we already taught you that Emax and E minimum. So this is the void ratio corresponding to loosest condition. This is corresponding to loosest condition. So I had to make the soil sample as a loose kind of stuff. So that means both the two are performed from in the field, yeah, in the lab. So both are lab tests. These two, for the value for these two, they are performed in the lab. The value of these two for the soil, they are performed in the lab. So your Emax can be calculated that you have that sample of soil. So soil sample is allowed to free fall from a height. So free fall from a height. So from a particular height you are falling that soil sample. So that falls, and the heap that gets developed, you can calculate the gamma for that. That would be gamma minimum. That is the minimum density we can have, loose density. After that, E minimum can be solved for if you have that if you have those what you call as soil sample, you are keeping that inside some bucket and you are going to vibrate that. So by the vibration we can say. So by the vibration they are coming to they become dense. Then densest state is achieved. Densest condition is achieved. So from that we can get the minimum value of void ratio. Then we say that if you assume that your solids are spherical, then for the condition of Emax, your solids are in this way. Emax, your solids are in this way. Such that your voids are in this way. There's some tetrahedral voids. So for that your Emax is actually equals to 0.91 I think, yeah. And if you talk about that I want E minimum, so I have to place the solids, I have to place those spherical solids in such a way that your voids are less. I have to ensure that voids are less. You can see that the void has become some sort of this triangular, what do you call that as, pyramidal or triangular. So this is your E minimum is equals to 0.35. So this is your two different values if you assume that solids are spherical. Solids of the soil are spherical. So we got this part also. Now we can convert this equation. In terms of gamma. We can convert this equation as an equation of gamma. So based on the equation that gamma dry is G gamma W 1 plus E. From that we can convert that relative density as a function of gamma. Now let's try to convert that. So we say that your gamma dry is a function of void ratio. So let's try to solve what is the value of E. Let's try to solve the what is the value of E. So that's actually G gamma W by G gamma W by gamma dry minus 1. Can we write that? So this is your value of E. If I say for the value of E max, your gamma dry should be minimum, and for the value of E minimum, your gamma dry should be maximum, and for the value of E natural, your value of gamma dry should be gamma dry natural. So for that, let's try to write the equation of relative density. Let's try to write the equation for relative density as E max minus E natural divided by E max minus E minimum. And let's substitute the equation value of E as that in this way we have wrote the equation. So let's try to write that E max. I would write your value of E max is actually G gamma W by gamma D minimum minus 1. So here the critical thing is that at the value of maximum we are having minimum value here, and after that we have the value that is minus natural. E natural we can write G gamma W by gamma D natural minus 1, and divided by that E max, that is G gamma W by gamma D. At that time your gamma D would be minimum. Gamma D is minimum at that time. At the value of maximum condition, void ratio of maximum, at that condition your density is low, so density is less. So after that we have minus of E minimum, G gamma W by gamma D max minus 1. Okay. Now we need to simplify it. We need to simplify this equation. I would say that your G gamma W is everywhere. So you can keep the G gamma W outside. This is everywhere. This is everywhere. This is everywhere. How can we solve it? Let's see. Okay. Let's try to write that we are having that G gamma W. In both the terms we are having that G gamma W in both the terms, and we can cancel the value of 1 because this is minus 1, and here we have minus of minus 1, so minus 1 gets cancelled, this part gets cancelled, so you are only left with that G gamma W minus G gamma W divided by gamma D minimum by gamma D natural. Similarly in the denominator also in this way, G gamma W divided by gamma D max. So we can cancel the G gamma W now. So we can say that this is your gamma D natural minus gamma D minimum divided by gamma D minimum into gamma D natural divided by gamma D max minus gamma D minimum divided by gamma D max into gamma D minimum. So we can solve that further. I would say your gamma D minimum gets cancelled with this part, so you are left with that gamma D max. This is your gamma D max divided by gamma D natural. We can keep it as small n, gamma D natural, and after that you are having that gamma D n minus gamma D minimum. That's our gamma D natural minus gamma D minimum divided by gamma D max minus gamma D minimum. So this is your final equation for that relative density. This is equals to relative density. Okay. So we can say that we are having this gamma D max here, and same value is also here, gamma D max. And we are having in the denominator the value of gamma D natural, and same value is also here, and this part is same, So we can remember it in this way. We can remember this in this way. Your gamma D max divided by gamma D max minus gamma D natural, your gamma D natural minus gamma min. That's your equation. Okay. Relative density. Okay. Let's try to take a problem for that. Let's take a problem. Let's go for the first one. Let's take the first one. That's we are having that what you call as sand from the field, and for that your unit weight is actually in terms of density that is 1746 kgs per meter cube. This is your density of that natural condition of that soil, sand soil. So your water content at that time, water content at that time water content at that time was 8.6%. Okay, and one more thing is there, gamma solids. This is the gamma of the solids. This is 2.6, and that was checked in the lab. This was checked in the lab. Okay, and one more data, that in the lab also, in the lab, let's remove this part. In the lab we are saying that E in the loosest condition, E in the loosest state is actually given to you 0.642. E in the densest state, E in the densest state is equals to 0.462. You need to calculate a relative density. Calculate the relative density. So based on the equation we need to calculate relative density. That is actually, what is the relation? That's E max minus E natural divided by E max minus E minimum. So our E max is there, E max is there, E minimum is there. E natural we have to calculate from this part. E natural. Can you calculate E natural? G gamma W 1 by E, 1 plus E. So from that we can calculate natural corresponding to that natural value. But this is the value. This is a value at some water content of 8.6%. So this is actually bulk unit weight. Can you say this is your bulk unit weight? As per the problem is saying that we are having some water content at that time. So this is your bulk unit weight of the soil in the natural condition, and that means your dry unit weight in the natural condition is actually, we have the relation that is actually gamma bulk of the natural condition, gamma bulk by natural, gamma bulk of the natural condition divided by 1 plus water content. Do you know that relation? That is gamma dry is equals to gamma bulk by 1 plus W water content. So we can have that concept here. We can have that concept. So we can write what is the gamma natural in terms of density. 1746 kgs per meter cube divided by 1 plus water content. That is 8.6%. That is 0.086%. In the fraction 0.086, I think. 8.6%. 0.086, yeah. This is your equation for that. And we need to say what is the value of G and what is the gamma W we know. So we need to say what is the value of G. So for that G, this is actually G solids. That is gamma solids by gamma W. Can you say that? So that's actually gamma solids by gamma W. And the gamma solids was given to you as 2.6. So that means we can say your G is actually 2.6. Your G is actually 2.6. Your G is actually 2.6. Yeah, this was your gamma solids. We can write this is actually gamma solids is actually, it should be actually gram per cc. It should be gram per cc. You can say in terms of density, your gram of that density of the solid is 2.6 gram per cc. That is it. Its unit should be 2 grams per cc. Okay. So we can substitute that value 2.6. So that's actually 2.6 into 1 gram per cc divided by 1 plus E natural condition. So your E natural would be solved that from this equation, that E natural is coming to be equals to 0.617. So 0.617. So that 0.617 is somewhere in these two values, in between the two values. So we can substitute that value here, 0.617. And E max was your 0.642 minus E natural divided by 0.642 minus 0.462 is equals to some value of dr equals to 0.1388. That is less than 15%. Can you say that this is less than 15%? So this is, we can say this is also 13.88% also. 13.88%. Or we can write your dr is less than 0.15. We have that classification of that soil is based on the ratio, based on that value of particular dr. So we can say that this soil is very loose. Can we say that? We can comment that soil is very loose. So your soil is in a loose condition, very loose. So your soil is a very loose soil. And from that, if the soil is loose, that means dr is less. If the value of dr is less, that means the shear strength is less and compressibility of that soil would be more. Compressibility of that soil would be more. So this is the conclusions we can draw for this kind of soil. We can comment, this is our comments on that soil. Comments on that soil. I would say your soil is very sad. It's not good. It's not good. It's your sad soil. Okay, let's take that. Let's take one more related to that same concept. That's your relative density. Let's go for that. It's saying that we need to calculate relative density. We need to calculate relative density, okay? And we are having a mold. We are having a mold. Mold of volume. Mold of volume is there. A mold is there of volume equals to volume of 100 millimeter, 100, or it's 1000 milliliters of that mold is there, and we are pouring sand inside that. We are pouring inside that mold the sand sample. So your sand, weight of the sand, if I fill that sand dynamically, that means by means of vibration, dynamically, is it by vibration? We can see that weight of the sand filled dynamically is equals to 2.1 kgs in this mold if I want to fill the sand in that. And similarly, your weight of the sand, if I want to pour it loosely, I want to make it in a loose condition, pour it loosely, that is saying that this is where the total weight is, it's only occupying that only 1.635 kgs is occupying that 1000 milliliters. That means less sand has been filled in the mold. So that's your loose condition, I can say. And third condition is there, that is the on-site condition, in situ condition. On-site condition, we have a dry density. We have a dry density of soil. Dry density of soil is 1.5 megagrams per meter cube, and your value of specific gravity of soil solid is 2.7. And assume that, and it's mentioned that assume sand to be saturated. For all that stuff, assume sand to be saturated. Assume sand to be saturated. Assume sand to be saturated. Okay. Now we need to calculate dr. So value of dr we know. Value of dr is actually E max minus E natural divided by E max minus E minimum. So can you get the value of E max, E natural, E max, E minimum? Can you get those values? I would say from the third statement, that is dry density on site, you can calculate E max, you can calculate E natural. Let's try to calculate that first part of the problem. We can calculate E natural. We can calculate E natural. Let's try to solve that E natural first, then we will see later. So E natural can be solved as your gamma dry in the natural condition is actually 1.5 megagrams per meter cube. That's actually G gamma W 1 by G gamma W by 1 plus E natural. So let's substitute those values here. So your value of 1.5 is actually how much? Is it I can say this is 1500 grams, 1500 kgs per meter cube. So your megagrams is actually 10 power 6 grams. So that's actually 10 power 3 kgs. Can you say that? 10 power 3 kgs. So this becomes 1500 kgs per meter cube. And that is actually G gamma W. G into gamma W. Gamma W is that 1000 kgs per meter cube. 1000 kgs per meter cube divided by 1 plus E natural. So get the value of E natural. Get the value of E natural. What is the value of E natural? What is the value of E natural? What is the value of E natural? E natural should be 0.80. Your E natural is 0.80. So we got one of the value as 0.80. So we got one of the part as 0.80. Now we need to say what is the maximum value and what's the minimum value of void ratio. Can you solve from this one? Can you solve? Should we write that gamma dry for the max condition is equals to G gamma W by 1 plus E for the minimum condition? Can we write that? And based on the data given to you, we can simplify. We can solve for that. But should we write this equation, or should we write one more equation, that is gamma dry max is actually gamma sat by 1 plus water content, and that's actually G plus E by 1 plus E into gamma W. What do you think? And we have to divide that factor also. Divide by 1 plus what you call as 1 plus W. Which of the equation we are going to use? Can you tell me? Based on the data, which of the equations you are going to use? Your weight is there, volume is also there, but this weight is corresponding to that soil is, that sand is saturated. That sand is saturated. So this is very important statement here. If the soil was dried, then we can directly write that G comma W 1 plus E, get the value of E. So that's your job to do. So let's then finally substitute those values. But here we are saying that this sand we are filling, we are pouring it, but the sand itself is saturated. Sand is saturated. So sand is saturated. That means we need to say what is the saturated unit weight we can have. What is the saturated unit weight? From that we can get the value of void ratio at that point. Void ratio at that condition. So let's go for that. Let's go for that. So let's write the first condition. That's the first condition, that gamma sat for the max value. Gamma sat max we can write. So first value we can write, first equation, gamma sat max. So I would write gamma sat max. Gamma sat max is equals to your G plus E minimum divided by 1 plus E minimum. At that condition, your E would be minimum. Your value of E would be minimum at that condition. Okay. Now this is actually gamma sat. We have to multiply that gamma W also. So this is your weight of soil in the that saturated condition. So that's actually weight of soil in the saturated condition. That is 2.1 kgs. 2.1 kgs divided by total volume of 1000 milliliters. That's actually 1000 centimeter cube. Is that 1000 milliliters is 1 liter? Can I say 1000 milliliters is 1 liter, and 1 liter is 10 power minus 3 meter cube. That's actually this one. So 1000 we can write 10 power minus 3 meter cube. 10 power minus 3 meter cube. So this is your 10 power minus 3 meter cube. So that means you got this one. Can you calculate now value of E minimum? Can you calculate value of E minimum? I think you can calculate value of E minimum from this one, from this equation. You can simplify the equation as a linear function of E, so you can get the value of E minimum equals to 0.545. And on the same grounds, on the similar grounds, we can calculate E max from this one, what you call as, we have poured the sand that is loosely, we have poured the sand in a loose way. So I can write second condition, gamma sat minimum. Gamma sat minimum is actually 1.635 kgs per volume of 10 power minus 3 meter cube. That is actually equals to G plus E max by 1 plus E max into that unit weight of 1000 kgs per meter cube. Into that unit weight of 1000 kgs per meter cube. And from that get the value of E max is equals to 1.677. 1.677. Okay. Now let's substitute the values here. 1.677 minus E natural was 0.80. 1.677 minus E minimum was 0.545. Your wide, that relative density is 0.7747. 0.7747, and this value is in the range 0.65 to 0.85. That means the soil is in condition of that dense condition. Soil is in the dense condition we can write. So that means shear strength and compressibility is shear strength is good, compressibility is less, we can write. Okay, this was the end of your relative density. Okay, this was the end of the relative density. I think we can stop that. This was the end of the relative density.